All right, so today we are going to look at the one new concept in hardware implementation, which is basically called resource sharing. So the basic idea of resource sharing we have already discussed briefly at the beginning of the course, right? The idea is that you have a finite set of resources and you time multiplex them. So you perform different operations on the same hardware at different instants of time. Okay, so this is sort of the exact opposite of what we were doing to improve throughput in the case of the parallelism and pipelining transformations, right? So just to sort of recap quickly how we got here, right? First we looked at representations of signal processing systems as data flow graphs. From there we said, okay, the ideal best case throughput that we can get, assuming infinite amounts of hardware availability, is determined by the iteration period bound. Okay, moving on from there we said, okay, if I don't have infinite amounts of hardware, what can I do? I can basically come up with an analysis which basically says, okay, assign a single piece of hardware to each functional unit or an actor, and then determine the critical path. That critical path in turn determines how long it takes for one iteration of that data flow graph to complete. Okay, once I have done that, then comes the question of how do I get my critical path closer to my iteration period bound, or in other words improve the critical path. And the way that we did that was two approaches we used. One was to parallelize the computation, use more hardware. Alternatively we said, okay, I don't want to add more functional units, I will add only registers, and by means of pipelining or retiming, basically moving registers around inside the data flow graph, I can reduce my critical path. Okay. Resource sharing on the other hand is looking sort of at the opposite end of the problem, right? It's saying, let's assume that I can run fast enough, I do not need throughput at this point, but I do have a problem with using up too many resources. I do not have the amount of hardware that is required in order to implement a completely parallel implementation or a fully dedicated architecture where each actor has a hardware unit associated with it. Okay. So to understand this better, let's start with a very simple example and then we will move on to a more complex example. The example that I am going to consider is just y of n equals a of n plus b of n plus c of n. The sort of trivial fully dedicated architecture for this system would look something like this, assuming that the hardware that is available to me is adder blocks that are capable of adding 2 values at a time. Okay, so that's a sort of fundamental assumption that I am assuming over here. I am not stating it, but rather in this case I am just stating it, but keep in mind that there are always some such assumptions that you are making before you even start with an architecture, right? In this case, the assumption that we are making is that we have available to us adders that are capable of adding 2 numbers at a time. If instead if I had some kind of a hardware unit that could straight away take in 3 numbers, add them and give you an output, then this entire discussion would be irrelevant. So one way that I could implement this looks like this, right, and it's probably the most obvious one that you would come up with if asked to draw an architecture for this. Why am I saying one way? Because obviously I can change the order of addition. I can do a of n plus c of n, then add b of n, or any of the other orders, primarily making use of certain properties of the arithmetic that we are using over here. Now obviously in terms of critical path, what I have is twice the delay of an adder, and the hardware requirement is 2 adders plus some wiring. For the most part, at least as a first cut, we are going to ignore the wiring, right? I am going to assume that the bulk of my area in my design is going to be occupied by the adders themselves. Now the interesting thing is, actually in modern designs that is not really true. Okay, in modern ASIC design we have now reached a stage where the interconnect, right, the wires that connect different hardware modules together occupies a very significant amount of space and accounts for a very significant part of the total delay through the circuit. Okay, so we in fact are hitting cases where the total speed at which a system can operate is not limited by how fast the individual gates can operate, but by how slow the wiring between them is. Okay, but I am going to ignore that for now and assume that if I have two hardware adder units, they dominate my area. A lot of this analysis sort of makes assumptions of that sort. In other words, it makes the assumption that my primary goal is to reduce the number of such hardware units. Okay. Later on we can sort of see, okay, if I don't have that, if I actually want to reduce wiring, if I want to reduce the number of multiplexers and all, how do I handle it? You basically treat them also as functional units with a certain area, and it's possible to build a model around that. But to keep things simple, I am going to just assume that the number of hardware units, the number of adders is what is going to be my primary determinant of area. So now let us look at the simple extension of this, which is to say, how do I convert this to an architecture where I have only one adder? So what would that look like? I have one adder available to me. What can I automatically say at that point? Is it possible to do both A plus B plus C in a combinational manner in a single clock cycle with one adder? By definition, no, right? Because the whole idea of a combinational unit is if you change its inputs, the output is going to correspondingly change and respond to that. Okay. So the only way that I can get something of this to work is I add A and B in one clock cycle, save that value somewhere, and in the next clock cycle I apply that as one of the inputs and C as the other input. Okay. So automatically it means that I have one number which I will just label as n over here, right, which is the minimum or rather the number of clock cycles to finish one iteration of the computation. And in this case I know that I need to do two additions. I have only one piece of hardware, one adder. What can I say must be the minimum value of n? What is the minimum value of n? I have two additions, one adder, 2. Okay. So n must be greater than or equal to 2, right? I need at least 2 clock cycles because I have to do 2 additions. On the other hand, the interesting thing is all that I can say is n is greater than or equal to 2, because if I gave you 3 clock cycles within which to finish this, you can still get the job done. Most likely one of those clock cycles will be wasted. You won't do any useful work during that time, but the answer won't be wrong. Okay, that is why we are writing n greater than or equal to 2 and not just saying n is exactly equal to 2. Alright, so in order to implement this A of n plus B of n plus C of n over a period of 2 clock cycles, my architecture is likely to look something like this. I have 2 inputs, therefore I will just mark them this way, and clearly at each clock cycle I need to change what is coming in as the input. The simplest way to do that is to use multiplexers. Okay. And what I can say is whenever the multiplexer select signal is equal to 0, right, I am going to apply A of n and B of n over here. Okay. Now in order to complete the architecture, what I am going to say is take the output of this adder. If I directly connect that back to one of the other multiplexers, that does not work because I will end up with a combinational loop. Okay, so I can't do that. So instead what I will do is I will just put a register out here. Okay, take the output of this and say now what happens when the select signal of the multiplexers is equal to 1, right. I am going to feed C of n in there and the output of this register to the other multiplexer, right. Keep in mind that I could have switched it around. I could have fed the output of the register to the top multiplexer and C of n down here. The result will remain the same, but the hardware architecture actually changes because the wiring that you have will actually be different in the 2 cases, right. So it's not that these 2 architectures are exactly identical, but we will skip over that for now. We are not going to bother. One last question to be answered: where and when do I get the output? Okay. So what I am going to say is I will further have one signal out here which I will call y of n, right, and if I directly take the output of that register, that is not really the value that I want for y of n, right. It is going to give me the wrong value because that register on one clock cycle is only going to have the value A of n plus B of n. That is not really the output that I want. So instead what I will do is I will use a switch, okay, and say that this switch will be closed for certain values of this select signal. Okay, so there is one select signal that goes to all three of these units, to the two multiplexers that are feeding into the adder and to the switch that is determining when the output can change. Okay. So, in order to understand the operation of this a little bit more clearly, let us look at the individual signals as they are going forward. Okay. So, I am going to basically label each of these nodes. I will call this in 1, this in 2, this one I will call it out, this signal here I will call it R out, and this one I will call Y. Okay. So, now let us look at the different signals as time progresses. So, what I have got over here is the top is basically showing the time instant, right, the clock cycle number, obviously starting from some arbitrary point in time and then progressing from there 0, 1, 2, 3, etc. The corresponding S value I am just going to write over here, right, will basically be that number that I have got on top over there, the clock cycle number modulo 2. Okay. So, in other words, what I am basically going to say is that S is 0 over here, 1 over here, 0 over here, 1 over here, 0 over here, 1 over here, and so on. Okay. So, these two are the sort of baseline that I am using for determining my multiplexer connections as well as my switch connection. Now, with this in mind, at time 0, what am I going to see at in 1 and in 2? The select signal is equal to 0, therefore, the multiplexer will choose the top branch. A0 and B0 will come as in 1 and in 2. Okay. Right. I am writing A0, B0 for A of 0 and B of 0, it is the same thing. And what this means is, with some short combinational propagation delay, during that same cycle, out will take the value A0 plus B0. This is combinational, that is why I am putting it in the same clock cycle. Okay. What can I say about R out? At time 0, I simply do not know what it is, it is X, undefined. So, I will just leave it blank. Similarly, Y also I do not know, because I do not know what was the previous state of the register. Okay. Now, move on to time 1. Select signal has become equal to 1. Okay. In 1 is going to be equal to C0. Okay. In 2 is going to be equal to the value of R out. So, I first need to know what is going to be in R out. Okay. And that essentially is coming from here, right, because after all R out is just whatever was there in out in the previous clock cycle. And that in turn is going to be present here. Right, which means that out is now going to take the value A0 plus B0 plus C0. The value of Y I still do not know, so I am going to leave it blank out there. Alright, let us move on to time 2. At this point I have A1 and B1 being fed into in 1 and in 2. The output of out is therefore going to be equal to A1 plus B1. What is R out going to be? It is going to be whatever was over here is going to come down, right. So, R out is going to take the value A0 plus B0 plus C0. So, this incidentally tells us, okay, this is a good time to take the value in R out and switch it over to Y. Okay. So, close that switch. Whenever S is equal to 0, close that switch, let the value in R out come on to Y, it becomes equal to A0 plus B0 plus C0. So, I can go up here and in this diagram I can basically annotate saying that when S is equal to 0, I close the switch, and when S is equal to 1, I open it. Okay. Alright, moving further, I will see C1 over here. This value A1 plus B1 will come down here. that in turn will show up as into, and that in turn will give me my output of A1 plus B1 plus C1 over here. I should make sure y does not change or is at least declared invalid at this point. Okay, so my simplest thing to do is just leave it blank. Okay, you can correlate this with our description of the so-called axis stream interface at some point, right? I mean, the axis stream interface, what does it say? Essentially, it says that if my valid signal is not equal to 1, don't consider the output. That's pretty much what I am saying over here. When S is equal to 1, ignore what I see at the y wire, whereas when S is equal to 0, I can say that whatever I am seeing on y is the actual output that was being computed from the previous set of samples. Okay, which is why I am just sort of saying that I can leave this blank. Another way of doing it would just be to say that when S is equal to 1, don't allow the value of y to change, don't let it reflect the value of R out. So you put a latch over there with half the frequency if necessary, that's all. Okay. We can take this further. At time 4, essentially I would have A2, B2, A2 plus B2, this would become A1 plus B1 plus C1, which in turn would come through to y, right? And at the next time instant I would have C2, A2 plus B2, A2 plus B2 plus C2, A2 plus B2, and y should remain blank. And in this way the entire sequence continues. Okay. So in other words, what we can see is this is what our hardware architecture would look like, and this time sequence that I have drawn below shows how it evolves with time, right? As each time instant passes, the select signal switches between 0 and 1, and depending on that, the multiplexers as well as that switch which is commutating the output will decide what value actually needs to come through to each place.